Ecological indices sounds like a scary word, but essentially it's just us doing simple calculations to try and get a feel of the richness, the balance, the abundance, and the diversity of ecosystems. So indices are simply calculations that we do using formula to figure out numbers that help us to model and describe our ecosystems. Now, there are a few here that we're going to go through and some that we're not. But essentially we're going to touch on density and diversity in this video. A few symbols you need to know, and I haven't actually written all of them down here, so I'm going to add some. First of all, little n is talking about how many individuals you have in a species. So the I stands for individual. Now you can also have a big N with a little I there, which is talking about the number of individuals, and it doesn't matter what species they are, it's just all of the individuals in an area, regardless of the species. A and V, I think you'll know, that's area and volume. Now here's another one here, P, usually with a little I after it. That is proportion. Now proportion is to do with the ratio of little n, the number of individuals of a specific species, to big N, the total number of individuals regardless of species. So you might have, say, in a riverbed, 2 crocodiles to a total of all crocodiles and fish might be 100. So a ratio of 2 out of 100 or 2%. Okay, so P is looking at the proportion of a species to all of the individuals in an area. Okay. Now density is not too hard to understand. Basically we're looking at living space here. How much living space does each individual have? Because living space is quite important. If it's restricted, number one, you end up with competition, especially between species because they're after the same resources. And it ends up with the weakest ending up being killed off in order for the strongest to survive. So living space is extremely important. So let's look at how we calculate it. We calculate it using density. So density, here's an example. I have gone out and I have sampled 100 quadrats. Every single one of them was 1 by 1 meter, which means in total that I have done 100 1 meter square quadrats. So my area is 100 meters squared. And in that area I found 1,000 dandelions. So on average, how many are in every quadrat? Let's have a look. I had 1,000 dandelions and I sampled 100 meters square of quadrats, which means if I cancel out my top and bottom, in every 1 meter squared I'm going to find on average 10 dandelions, and we call that our density for that species. Okay? So that's how you work out density. Now diversity is really important too. That's looking at the abundance and the richness of the species in a specific area. And we're going to be using Simpson's diversity index to look at that. Essentially, Simpson's diversity index calculates the chance of, if you pick out 2 random individuals, what's the chance that they're going to be the same species or different? That's what it essentially picks out. So if you have a really diverse number of species in an area, and you randomly pick out 2 individuals, the chances that they're going to be exactly the same species is going to be really low if you have a lot of diversity. However, if you have a very high, an area that doesn't have a lot of different individuals, it might be, say, okay, a wheat field. You might have mostly wheat and a couple of weeds. If you randomly pick out 2 individuals out of that field, what's the chance that they're both going to be wheat? Well, it's going to be very high. So on the Simpson's diversity index, the higher the number, the closer it is to 1, the lower the diversity. And the lower the number, the closer it is to 0, the higher the diversity. So you've got to get your head around that. So let's have a look. First of all, it has 2 different components. The richness, that's how many species they have in the area, and the abundance, that's the number of individuals in every species. So let's have a look at that. I just told you what richness is, and abundance. Abundance is that little n I was talking about before. That's your tally or your count of the individuals for every species. And when we look at this abundance, we turn it into what we call relative abundance, which means what's the ratio of my individuals for that species to all of the individuals in the species. Okay, so if I had, like I said above, 2 crocodiles in an area where I had 100 individuals, and it doesn't matter what they are, fish, crocodiles, anything, that means that I had 2% or 2 out of 100 crocodiles in that area. We call that the proportion, or P, of crocodiles in that area, 2 out of 100, or 0.02. That's the proportion of that species, the crocodiles, compared to everything else. Now we take this into account when we calculate Simpson's diversity index. So here's how you calculate it. It looks quite confusing, but it really isn't when you break it down. First of all, you have to have the sum, that's what this word thing here means, the sum of all of the individuals that you have in an area, and each one of their numbers is squared. So basically you do a count of your crocodiles, a count of your fish, a count of your snakes, and each one of them has a little n value. That's the number of individuals in that species. You square those values. Forget about the -1 for now. You square those values together. So we're going to go over an example of that in just a second. Then you have to compare them to the proportion of all of the individuals in the area, regardless of the species they are in. Okay, so we do a count in the area of all the individuals, doesn't matter what they are, and we square those values as well and put that on the bottom of the fraction. Then, to see how far it is from 1, we take it away from 1. Now you might be asking why we have this -1 up here. Well, it's quite complicated to get into it, but essentially that's a biological fudge factor. When you count individuals in an area, you rarely count every single individual. We usually have sampling. We usually take lots and lots of quadrats and we count a selection of the individuals in that area, and we hope that those quadrats are a representative of the area that we're trying to figure out and sample. You can't count every individual ant in an anthill. You wouldn't even want to try. All you can do is sample it and hope that you've got enough samples to get an accurate guess. Well, by taking that one of those n's and minusing 1 just from the actual top value, you actually help to bring that estimate closer to what reality is. We can actually show you this in action. We can actually show you people doing this with numbers to show that it does work. But essentially, as soon as you start sampling to guess the number of individuals rather than counting every single individual, you have to add in that fudge factor. And like I said before, a high number close to 1, okay, means that you have low species diversity, and a low number, which is close to 0, means you have high species diversity. And that can mean several things. Closer to 1 can mean that it's either very stressed and a lot of things are starting to die out. It could mean it's in a very simple food web with not a lot of individuals to begin with, like a desert food web compared to a very diverse one, which would be a forest food web. It could mean that there are some serious changes in the environment, like pollution, that are causing ill health and change in the diversity of the species in that area. And the opposite, it can be said, of course, for high species diversity. So next video is going to take you through exactly how to do this and give you some examples both by hand and with Excel.